supposed to remind me. You're supposed to remind me. I about started without recording.
Don't forget to record.
All right. Cool. All right. So we talked about at the end of last week, talked about importance of screening data, right? The absence of knowing what your data is doing, you can start to make inferences that are not warranted at all. So always want to go through, look at your data in terms of summary statistics. One of the things I'm going to say as we're working through this, we're going to give you guidelines, benchmarks, and things like that to go through and look at that. But like anything else, these are not line drawn in the sand. If we're on one side of it, it's terrible. If the other side, it's okay. Always wanting to think about this as continuous evidence for, is there something wrong, right? And then the question is this perfect? The answer will always be no, because we never have perfect data. The question is to what extent is this going to screw stuff up? To what extent is this going to start to impact my inferences? And do I need to do something about it? And is the thing that I could do about this, does that make it worse or better? Sort of depending on how we're setting things up. Okay. So that's kind of the thing that we're thinking about. When we think about some of the screening that we've done to this point, is my data normal or not normal? That's not a reasonable question, right? It's to what extent is it not normal, right? To what extent do we have deviations from normality, and then are those deviations going to be something that's problematic, right? So thinking about things in terms of degrees and severity as opposed to yes, no decisions with things. Okay. Also thinking about getting a good sense for what my data say, and looking at that to get that giving us valuable information about my design, my data collection, my variables. Are things doing what they should be doing? There's such rich information to be pulled out of this if you start looking at this and thinking about what you're doing as you're working through stuff. Okay. This first series of slides, this is going to be really straightforward because we've already went through it, right? We're always going to take a look at accuracy, plausibility. Like, are we in the expected range? Are our variables coded appropriately? Do I know what variables are? Robert and I were just talking about, so Robert sent me a condition variable or something like that. So I need to know what numbers correspond to what conditions, right? And making sure everything kind of plays in. If I've coded categorical things like gender identity, do I want to know what those labels mean? Making sure that everything sort of makes sense. Do I have variables are appropriate? Do I have the expected number of cases? These are all things that we're going to go through, take a look at our frequencies, our descriptives to go through and make sure everything squares up. Okay. Also going to look at missingness and think about missingness. And as we start to get into more complex analyses, wanting to think about missingness in a way that's a little bit more nuanced than how many cases have missing data. That's important, but then also thinking about the overall pattern of missingness. We start to get into more complicated analyses. We talk about ignorable and non-ignorable data. If I have data that's random and not overly pervasive, we can also talk about this as ignorable missingness. Like, okay, yeah, I've got some missing scores, but it's not something that I'm expecting to impact my data, my analyses, or any of my inferences. If I have non-random missingness, now it starts to impact the interpretations I can make in the potential generalizability of my results. Okay. When we talk about missingness, there's kind of a framework that we use to think about more so when we get into like SEM types of things where we have an estimator that'll account for missingness, but still starts to become relevant in regression and things along those lines. Kind of a way of categorizing or qualifying our missingness. Missing completely at random, MCAR. If my data are MCAR, that means essentially this is consistent with our idea of randomness, right? Like basically there are just items that are missing throughout or values that are missing throughout my data that are based on nothing. They're unrelated to anything. It's true random missing data. From a statistical standpoint, we would say that the probability of the presence or absence of some given value is independent of all other variables in the set, including the variable itself, right? So if I'm missing values for extroversion, that missingness is unrelated to any other variable that I've got or haven't collected. It's also unrelated to the level of extroversion. It's just a completely random occurrence that's going through. And this is what we typically think about in terms of random ignorable missingness. We also have a second type of missing at random, MAR. And here we've got a situation where the presence of or absence of a given value is dependent on other values in the set, okay? But unrelated to whatever the variable is after I control for that outcome. So basically what we've got with missing at random is it's not missing at random. It's actually systematic missingness. There's a reason that those data are, or those values, they're missing for a reason, right? But the reason they're missing, or whatever the mechanism is that's causing those to be missing, is something that's already we've captured in our data. So if I know what the value of X is, or some combination of X's, I can predict whether or not Y is going to be missing or not, right? So it's not random. It's dependent on the X's, or sort of associated with the X's. Well, once I go through and I account for that, then whether or not I happen to have a value or non-value for Y after I control for those X's, then the missingness has nothing to do with the actual value of Y that I'm missing. Yeah.
So for this one, for the missing at random, it also kind of be dependent on other dependent variables.
Yep. So basically what we've got in this situation, I have missing values in my data, but I know why it's missing. And and I've collected data variables in my data that account for sort of the missingness in there, right? And so there's that handout I sent you. Take a close look at that. Also read that Schaefer and Graham paper carefully, because it's a really, really good way to sort of start to solidify ideas around this. They've got repeated assessments of blood pressure sort of in that. And in one of those, they're missing at random is, okay, so we've got blood pressure at time 1. And then if for everybody who has blood pressure less than a certain level, we didn't collect it at time 2, right? So we would say that that was missing at random. It's not missing sort of completely at random, because anybody who had reasonable blood pressure at time 1, we just didn't collect it at time 2. But we know that blood pressure collection, the presence or absence of blood pressure assessment, whether it's there or not at time 2, is basically dependent on the measurement we already got at time 1. So basically that's recoverable information. We know why that we're missing this, and the reason why is coded in our data. What we've got there is then our data are MAR, right? Statistically, we can account for that. And once we control for blood pressure at time 1, the missingness is unrelated to anything else or the value of Y, okay? So this is a different, missing at random doesn't mean completely missing at random. It means that sort of the missingness we've accounted for by other stuff in our data. And so this is okay. We can handle this. Where we get into problems is when we have missing not at random, okay? Missing not at random means that the probability of the presence or absence of some value is dependent on the true value, right? Maybe on some X's as well that maybe we haven't measured, right? So if I've got values that as these values increase, they start to become increasingly less likely to be captured, then all of a sudden we've got a problem, because what we're going to do is we've got a sample of data, but we're systematically missing values for those individuals who are high on this scale, and we don't have other variables that account for why we have those missing values, okay? This starts to become a problem, okay? For clinical folks. This is one of my personal soapboxes when we're thinking about looking at treatment outcome data, right? We'll go through and we'll use models that account for missingness in our data, right? Because some people are going to drop out of treatment, things along those lines. Problem is those techniques assume at least MAR. Whether or not people stay in treatment is not missing at random, and we don't have good predictors for why people don't stay in treatment. If we did, we could address it, but we don't. Some people just aren't going to go through and complete treatment, and that's probably a non-trivial pattern of sort of characteristics. So what we do is we use techniques that account for missing data, but the assumption of those estimators in terms of if they're giving us valid estimates are assuming missing at random, but our data most certainly are not missing at random. And so what ends up happening is we're predicting outcomes and trajectories for people who didn't complete treatment based on data we have collected for people that do complete treatment. But the people who do complete treatment are systematically different than the people who don't complete treatment in important ways, but in ways that we don't understand and probably haven't included in the data set, right? And so what we're start to do is we should be concerned about the validity of our estimates, because basically we're projecting out, oh yeah, this is probably what this person would do, but our estimates of what this person would probably do is based on people who have completed treatment. Those are people we have data for, right? And so you can start to think about how this starts to become problematic in terms of estimation, okay? So thinking about when you have data, hopefully it's just because some people don't fill out questionnaires appropriately, or I didn't start collecting some measure until halfway through the study, and so I'm missing for all of these, but then I did, so I know why it's missing is because I just didn't start collecting things. But always wanting to go through and think about when we go through, take stock of our assessment or our missing data, always be thinking about where is this coming from? Why are these values missing? Is it look like it's related to anything else in our set, to try and account for what's happening with our data, so that we just don't ever assume that everything is ignorable when it in fact might not be. Okay. So thinking about if anybody's like doing physiological stuff, right? And I start losing data as sort of levels gets very high or very low or something like that, right? That's a problem, right? Because the missing value is dependent on the value of Y. Like if I would have collected this person's blood pressure, that blood pressure would have been quite high, but I lose it because something's wrong with the calibration of my thing. And so missing this is dependent on the variable that I'm collecting. And so now all of a sudden I've got problems with potential biases and things like that. Okay. So go through, take a look at that sheet, make sure you look through that Schaefer and Graham paper. That's a very good paper and sort of takes on kind of a difficult concept to wrap your head around, but thinking about missingness, what's the mechanism starts to become important with stuff. Okay. Questions? All right, cool. Distribution assumptions, we talked about this before. Univariate normality is what we always are looking at, sort of are things sort of univariate normal. With our group-based analyses, we are pretty liberal in terms of what we're looking at, because we actually don't have strong assumptions about the distribution of the observed data. We have assumptions about the distribution of sample means. But as we start to get into regression models, now all of a sudden the distribution of the observed data does start to become important for reasons that are complicated that we'll get into. But as we start to get data that are non-normal, it starts to cause us problems, right? So we want to be thinking carefully and looking at that. We also talked about multivariate normality. This becomes important in regression because we consistently violate one assumption, which doesn't cause us any problems as long as our data are multivariate normal. And so we need to start thinking about, do I have evidence of multivariate normality within my data? For multivariate normality, we're assuming that every variable and all possible linear combination of variables are normally distributed. Again, this is an extension of our bivariate normal distribution that we had talked about, right? Here we're assuming for all values of Y, X is distributed normally. For all values of X, Y is distributed normally. We have this kind of linear relation here in this graph. Multivariate normality takes this into another level, because now we just don't have two variables to look at in terms of multivariate or bivariate normality. We've got 3, 4, 5, 6 different variables that all need to be working together in concert. This is difficult to test directly, but we can make assumptions about if certain bivariate distributions hold. We can make assumptions about multivariate normality. So we have to test this indirectly. But as soon as we start to get very skewed distributions or things that start to look wonky, this will start to throw that off. So we need to, and we'll get into procedures for testing multivariate normality stuff. So most of our univariate, multivariate tests, we've generally assumed that those are fairly robust, and there is some evidence to suggest they are robust, but then also some papers that are suggesting that they're maybe not as robust to violations of normality than maybe we've thought. This is sort of, as we've gotten better techniques for dealing with this has started to come into question more and more, to the point when we're getting into like SEM types of frameworks There are arguments that you just use a robust estimator regardless, because if your data are normal, it converges with sort of your normal estimator, and if it's not, it sort of comes in and makes adjustments. So we have better tools for addressing this, but always wanting to go through, take a look and say, do I have a problem? To what extent is this a problem? And do I know why this problem is occurring? Sometimes we do, sometimes we don't. Just because we know why a problem is occurring doesn't make it not a problem, but at least we know why it's happening. Okay. So again, always test your assumptions. We're going to do a lot of tests with regression that people often won't do, but probably should, just to make sure that you don't have results that are driven by one or two cases that are sort of driving things way out of bounds. As we start to get into moderation analyses, this is particularly problematic. Even if you do have big samples is generally our guard against like one person really throwing things around. But in regression analyses, even with the types of data that we're using, particularly if you're running interaction models, one or two cases can start to drive interaction terms and things along those lines. So it's an important thing to take a look and think about. Okay. When thinking about distributions for our group versus our ungrouped data, a little bit of different approach. For our ungrouped data, okay, this is going to be our regression types of analyses, our continuous analyses. We are going to assume multivariate normality if each variable follows a normal distribution. Okay, so now all of a sudden we are start to become more concerned with the observed distribution that we're seeing. With our group-based analyses, we can say, oh, well, we're distribution of sample mean, so we don't care so much about what the actual observed data are looking like. For regression, now we do, because we need to assume multivariate normality or test multivariate normality. And so we're assuming if we've got all of our variables that are continuous, follow a reasonably normal distribution, and our bivariate relations are linear and homoscedastic, we'll talk about what that means. Then we can reasonably assume that our data are multivariate normal. But if our variables, observed variables, are skewed, or we have heteroscedastic relationships, which we'll talk about what that looks like. Now all of a sudden we can assume that our data are multivariate normal, and so some certain things sort of kick into play, right? We are basically violating our assumptions of regression. Okay. For our grouped data, our normality assumption again pertains to the sampling distribution of the sample means, okay, not the observed variables. We've talked about this all last semester. If we're doing t-tests, ANOVAs, things along those lines, and we get wonky distributions, we shouldn't panic. We're not too worried about it, so long as our cell sizes are reasonably large, so long as we don't have extreme values that are dragging out my mean estimates around and things along those lines. So here, having nice, normal, clean distributions is less important than having reasonable representation, right? If my sample size is reasonably large, generally, there's some disagreement on this, but generally we would conventionally assume that our data, our analyses are relatively robust to weird distributions in the observed variables, okay? Questions about this? Based on our analyses, a kind of a different approach to how we're thinking about potential problems with the distributions of our variables. All right. Univariate normality, you all know this. Skew, this is the symmetry of our distribution. Positive skew, we got tail out going towards higher ends. Negative skew, tail going out towards our lower ends. What we're concerned about here when our our distribution starts to get extreme is that our mean is no longer a valid measure of central tendency. It's that mean is getting drug out towards my tail, okay? If we think about in a classic skewed distribution, how the mean, median, and mode all fall out, mean's going to be out towards the tail, modes are going to be towards the body of the distribution. And this is why median will generally be in the middle and is generally considered your best bet for measure of central tendency for a distribution that's fairly skewed. Okay. Kurtosis, again, this is thinking about shoulders and peak of your distribution. Positive kurtosis. Here I've got heavier tails and a higher peak. What is our what is a classic example of positive kurtosis? What kind of distribution? Do you remember?
Oh wait, no, I was gonna say like dichotomous variables.
Okay, well, that's not really a distribution because you just got two variables there, right? What is what is a good example of a positively kurtotic distribution that we know and use all the time? Guesses? Our t-distribution. T-distribution is positively kurtotic, right? We've got kind of a skinny, relative to our normal distribution, we've got kind of a skinny peak and then flat tails that kind of come out, right? So our t-distributions, particularly t-distributions with low degrees of freedom, these are classically positively kurtotic distributions, okay? And we know that it's not a problem with the t-distribution because z is normal, t gets normal as degrees of freedom increases, but particularly at low degrees of freedom, we've got that skinny body and kind of heavy tails that go out. Okay, negative kurtosis. Here we've got flat and center, heavy shoulders. If you've got a uniform distribution where everybody's kind of like all values kind of have the same, you have the same representation across all values. Something that would be a non-random or a fixed effect variable, something like that, where I've systematically sampled individuals for all possible values. Then I've got a square distribution that's going to be a kurtotic distribution, right? You can think about this as kind of being kind of rounded like this. Okay. Remember that our kurtotic distributions tend to underestimate the population variance, right? If I've got a sample that has either sort of extreme positive kurtosis or extreme negative kurtosis, my concern is that I've gone through and underestimated the variability. With my positive kurtosis, I'm missing those shoulders because everything's kind of set up here in the center. If I've got a negative kurtosis, I'm missing the tails. Either one of these, I start to become concerned that I've underestimated the variability of in the population, which can bias my parameter estimates and my standard errors. Okay. So when we're thinking about how do we go through and gauge the extent to which skew into kurtosis is problematic, right? It's always going to be there present. Well, I'm never going to get my distribution popping up at 0 that everything's perfectly normal. That's never going to happen, right? We're always going to have some skew, some kurtosis, but we're always going to be careful and should probably never even really consider our tests or significance tests for skew and kurtosis. Why are we not interested in these? So if I find a test and it says that I have significant kurtosis, what does that mean?
It's just like the probability of kurtosis instead of like, it doesn't really tell you like the direction, or it doesn't really tell you anything. It just.
Okay, the probability of what?
Oh wait, never mind. So it would be the probability of another study.
Well, kind of. I mean, because we got a p-value attached to it. If I say that I have significant kurtosis, what does that mean? What does any significance of a test tell me?
That it's not 0.
Yeah, it just says that my kurtosis is not 0, right? Do I care if my kurtosis is 0? No. As my sample gets increasingly large, what happens to the sensitivity of that test? It increases, right? And so this is what happens. I would sometimes be reviewing papers and someone will get like, oh, I had significant skew in these data. And so we did a bunch of transformations, right? I'm looking in the sample size like 300-400. Like, well, right. So I would hope you had significant skew, right? At that level, probably any deviation from sort of 0 value is going to tell you you have significant skew, right? It seems like it's a bad thing. and it's probably not, particularly if you have the sample size to power that thing, right? And so again, it's this reliance on tests and p-values without thinking about what they actually mean, right? So as my samples, particularly for regression and some of these types of analyses, we should be using relatively large samples, and so we should have relatively sensitive tests. And so I really don't care if I have evidence that my skew or my kurtosis is not 0, because that's not my assumption. So it's actually not terribly informative of anything, right? What I'm going to get more information from is looking at my indices of sort of how extreme is that skew or kurtosis, and looking at my sort of distributions to kind of see what's going on with my data. Okay, so here we think about skew and kurtosis less than 2 being a general kind of guideline. So examples I might talk about this: values of skew and kurtosis were acceptable in these data. If I got like 4 or 5 variables, I'm just sort of giving absolute values, kind of giving the magnitude of my skew and kurtosis indices. I'll say they're acceptable. Skew or kurtosis values fail to provide evidence for problematic deviations from normality, right? I'm not saying that my data are normal. I'm just saying that the level of skew kurtosis is probably not going to be a big issue for what I've got going on. Okay. Now, if going through and looking at data, like if I have a skew value of 1.5, what does that distribution actually look like? It could look pretty nasty, right? So again, to say just because my skew value is less than 2 is telling me that my data are normal, that's absolutely not what's happening, right? My data can look very obviously skewed and still have a skew value under 2, right? So we want to be careful in how we're describing this. We would just say, based on the sample that I've got and the size, that it's probably not going to be an issue. My data will handle this piece of things, okay? So skew less than 2, kurtosis less than 8. I mean, you start looking around, you can find benchmarks that will accommodate pretty much whatever you want. We're going to be less concerned about that and more concerned about the functional impact on our results, right? So as Tabachnik and Fidel note, hopefully as you read in that chapter, again, that chapter, thank you all for going through and reading that. I apologize for forcing you to take a quiz to make sure that you did that, but there's just so much information contained in that. Tabachnik and Fidel say positive kurtosis negligible at samples of over 100, negative kurtosis at samples over 200, right? So again, as we start to get larger and larger samples, we get better at tolerating some of these deviations from normality with larger samples. So again, looking at our histograms, always wanted to take a look at saying, what does this look like? Sort of where are our skew? How severe is it? Running through histograms, also sort of identifying extreme values. If I've got some case that's hanging out way beyond the tail, I've got sort of my distribution, and then sort of steps over here, I got someone hanging out. Starts to give me an identify. So basically, when we're doing these analyses, I got to have a running list of suspects, right? I'm like, okay, case number whatever came up as an extreme value, falling away from the rest of the distribution. Same case keeps coming up again and again. That starts to become an increasing candidate for maybe we sort of leave this person out of the mix, unless there's a good reason for them to be in there. For a group-based analyses, again, we generally sort of think about our group-based analyses as being robust to violations, although there are strong arguments that this may not be as robust as we might wish they were, but generally, conventionally, we're saying things 25, 30 people per cell, we're doing pretty good with that, right? So, I mean, those are reasonably sized cells for experimental work, but they're not unachievable, right? So in terms of just thinking about power for designs, and so what do I need in terms of representation for different conditions in order to start to make me less concerned about possible violations of normality and things like that, kind of gives you a target-ish to shoot for, okay? Circumstances in which our analyses are not robust, again, not news, we've talked about this before, but if our distribution across groups is a different shape and different variance, right? Basically, if I've got severe skew going in opposite directions, This doesn't happen a whole lot, right? This is kind of a weird case, but if it does, something that you might want to be starting to think about, boy, do I have an issue. Different sample sizes and different variants, right? If my larger sample has a larger variance, I'm going to get tested or too conservative. If I got a larger sample with smaller variance, I have too liberal of tests, right? This is all sort of based on the standard error, right? Now, because when I go through and I calculate that standard error, I'm using pooled variance. And if I've got a big sample and a small sample, which one of those samples gets more say in terms of my overall, my pooled variance? What do you think, Josiah? Yeah, bigger one, right? Because my assumption is under my t-test that we have equal variances. And so I'm saying, okay, well, this one's bigger and that one's smaller. The bigger sample is a better estimate of the common variance across these two. But if I have a violation of homogeneity of variance where the populations do have different variance, the one with the bigger, the one I've sampled more gets more say in the pooled variance. And so it starts to become a problem with things, right? If I have small sample sizes and violations of normality. So again, remember that for our group-based analyses, we're generally okay if we've got one violation, but if we start combining them up, that's when we start to run into problems and start to have concerns about potential impacts. Now, do we not do the study? Do we not do the analysis? We just throw up our hands and say, well, I guess that's no good. Probably not, right? But what we should be doing is thinking about the potential consequences, right? Is this combination of violations something that's going to make it less likely for me to find something or maybe more likely for me to find something? If it's that, sometimes we might be motivated to kind of ignore it because it's doing what we want it to do, but that's not great because of problems with replication and things along those lines, right? So not just, yeah, we have a problem, thinking about what is this problem likely to do, and then how does that influence how I'm interpreting my data? All right, outliers, which I need to change this to extreme values because I don't like outliers. Outliers is kind of a qualitative yes, no type of a thing. But if I got a univariate outlier, these are easy enough to describe. These cases pop up, are very easy to detect because they're just like hanging out there on the margins, right? But when we start to get into multivariate space where we were working with multiple variables, now all of a sudden we've got to be considering the potential for multivariate outliers. Okay, and if I'm looking at talking about a multivariate outlier, what I've got here is a case that's weird, not because of one score, but because of a combination of scores. So let's say that I'm looking at some data, right? And I've collected age, income, and sort of region, like sort of where people are sort of located, right? If I'm just doing a general survey of the population, if I have someone who's 10 years old, that's not a univariate outlier. People are 10. So lots of folks are 10, right? If I have someone earning, say, 130,000 a year, high income, but there's going to be people who are going to be that's on the high end of the distribution, but it's not going to be. I'm not going to identify that as a weird case. I could identify folks living in the rural South. That's sort of where people live, right? That happens, right? But if I throw all those things together, okay, if I get a 10-year-old in the rural South with a documented income of 130,000, now all of a sudden that's a weird case, right? That's a case that because of those combination of variables, that person's a multivariate outlier, right? It's a combination of things that don't typically go together within our case. That's not saying that they're not a real person or it's an error in our data. It's just someone who our model may not generalize to. And so it starts to become important to identify those folks, understand what's causing them to register as multivariate outliers, and then try and make a decision on whether or not we want to keep that person in our set or not. Some big decisions here, okay? Do people understand sort of this concept of multivariate? So like individually, I'm fine. Like if I go through and look at my individual distributions, not a problem at all. But when I start to look in multivariate space, now all of a sudden I got someone hanging way out here who doesn't make a lot of sense based on everybody else in my set, okay? People comfortable with this idea? All right. So possibilities, possible things, because anytime we find an extreme value, I want to be thinking about what's going on here. How do I understand this? Well, one, I might have incorrect data entry. This happens all the time, right? We've got RAs entering data, we're entering data, we miskey something. All of a sudden we've got a value of 99 in my data set so that's not a real value, or doesn't seem to be a plausible value. So want to go through and say, was this something that was just misentered? Failure to specify missing data codes. I would do this all the time in SPSS because I use 999 as a missing data code. But if I forgot to tell SPSS to read 999 as a missing data code, what I end up with is a really crazy distribution histogram. Everybody's like from 1 to 10 and then sort of 1,000 way out here, right? So thinking about like, do I have a code in there that should indicate a missing value that I haven't told the system to register? And then if I start calculating means on that, now all of a sudden I got means that don't make any sense, right? So taking careful stock of that. It's also possible that data entry is correct, and so it's not a missing value. It's just person's not an intended populated member of my study, right? Again, I think if I'm looking at income in young adults, and so I'm looking at sort of income from sort of work study stuff from university undergraduates, right? And now all of a sudden I get someone who's making $150,000 a year, and I go through and take a look, and this is maybe someone who's retired and coming back in to sort of get education. They've never been to college, but they're technically a freshman, but they're 65, right? All right, that person probably isn't someone who I'm interested in looking at, right? That's a different person. Their situation is separate. I'm going to toss those people out. So I'm not saying that this person isn't a real person. It's just not someone I'm trying to generalize to. And so I'm going to go through and get rid of that person. We can also have situations where person is someone who's of interest. They're just if I'm thinking about, particularly, and this will particularly happen in small samples, right? We got a small sample. If I'm looking at eating pathology or substance use or something along those lines, right? If I'm, say, looking at cocaine use, right? Like you maybe see a little bit, but then maybe you capture somebody who's a heavy user. But I'm assuming that's heavy cocaine use is probably pretty rare to capture in like a university sample. And so maybe that person is someone who I'm interested in, like this is a heavy cocaine user, and that's actually really important person for me to be thinking about. So they are an intended, it's just, I'm not going to get very many of those unless I've got a really big sample. And so, yes, I understand why they're an important person I don't want to throw out, but maybe I have to think about different ways of keeping them in that doesn't screw with my analyses, because that person is too influential and starts dragging things around. Consequences of my outliers have impacts on my coefficients. Inflation of type 1 and type 2 errors, I just don't know. Like they can make things look really good, they can make things look really bad. The problem with extreme values is we can't predict what it's going to do. Some of the other stuff, heteroscedasticity, sort of other types of things, we can say, okay, we can go through. Generally, if this is what's going on, we know that this will generally tend to be the issue here. With extreme values, it's free for all. Who knows what they're going to do? And the real concern is they start to impact the generalizability of our solution. We've estimated a solution with that person in there, but I don't know if this solution is going to generalize to anybody else because it's being skewed by some extreme values. Okay. Now, the types of work that we do, we're in a better position than some other people in some other areas where they're looking at real life outcomes that have no limit or real bounds in terms of what they're doing. Like we can have extreme values, but our extreme values are generally limited by our assessment instruments. Someone can only get so high on self-handicapping because self-handicapping has a limit to the top of the scale that you can have it at. Like you can't have a self-handicapping score of 8 million because that's not real, right? But if we're looking at income, sort of prices, sort of other types of things, it starts to become population and things along those lines. That starts to become problematic, right? It's less so with us, but still something we want to be thinking about.
So like essentially with this one, if you keep the extreme values in, it's instead just like you're describing your sample more so than like the actual population that you're interested in. Like
yeah. But again, like you're thinking about like sort of what's generally going on in my sample? Well, what's generally going on in my sample is this, but if I throw this person in the mix, it makes everything look like it's a lot higher than it is based on one person, right? So even talking about what's going on in my sample is actually biased, because if I'm looking at what most people are doing, most people are not using cocaine. But I got this person in, and it makes my data look like some people are using cocaine when actually not. It's just one person is using a lot of cocaine. Everybody using no cocaine. And so the average is that people sometimes use cocaine, right? So wanting to think about what's happening with the data and sort of how do I interpret it? Like, what are my data actually saying? Is that a reflection of what's actually happening in my sample? And so this is going to be where, if I'm going to do that type of thing, I'm going to need to be thinking about, okay, well, I'm going to have to get a large sample if I'm going to capture people. And then if I do capture people, that the people that I've captured don't screw up the whole study because they're sort of really high. Questions? All right, cool. And I know this is a great discussion because it sort of really highlights sort of the conjunction between statistics and methodology. Like you can't run statistics without thinking about your methodology. Like you can. It will just be probably not good and result in misleading inferences, right? So you have to be thinking about these two things together. Identification of our univariate outliers. Thinking about univariate outliers and our dichotomous variables is not something we typically do, but if I've got splits 9-to-1, right? That's probably an outlier, right? If I have 90 women and 10 men in my sample, men are kind of an outlier in the sample. Like I've got hugely unbalanced data. What happens is those 10 men start to have a larger influence on, like any one of those 10 men have a much stronger influence on my model than any single woman in the 90, right? And so we start to have a problem. Like, yeah, there are more women. And so sort of results are being driven primarily by women. But if we're thinking about the relative impact of any single woman and any single man in that study, the man has a lot more power and influence on the solution than any one woman, because all the women are sort of in the combined, and sort of you only got these many, just a handful of men. And so it starts to have undue impact on sort of things if we have these types of splits. These uneven splits starts to result in the attenuation of associations. Sebastian, I'll talk about this. If I've got really uneven splits, it can start to make the correlation between my dichotomous variable, my continuous variable, look weaker than it should, just because there's not enough representation in one thing. So are probably underestimating associations. And so unless whatever variable that is, if it's not critical to your analyses, you should probably think about leaving it out, right? Like, boy, this is a thing that I'd really like to take a look at, but I just I haven't captured the representation of sort of group B relative to group A. I could throw it in, but it's probably going to cause more problems than it or answers. I would like to look at this, but even if I look at it, I'm not real confident that the answers I get are going to be reliable or credible. So if it's not something that absolutely needs to be in there, probably think about, well, probably won't, sort of maybe we'll leave this out and think about, hey, next study, if I want to really look at this, sort of try and devise some strategy for reasonable data collection across the board with that, to get something that's a little bit more even. For our continuous variables, think about these as operationalizing these as extreme scores. If we've got large samples like we should have for our regression models, setting a value of like 3.2, 3.3, you'll see people use that as sort of associated with the probability of p less than 0.001. Here we're talking about something that's about getting close to 3 1/3 standard deviations from the mean. That's starting to get pretty far out there, right? So again, kind of a general estimate, sort of a marker that we use. Now, we wouldn't say, oh, hey, we've got no extreme values in our data because all my z values were 3.28 and above, and then make a different decision if it's 3.3 and above, right? So again, wanting to think carefully about this, but a nice way to go through and at least quantify how extreme are our extreme scores, okay? And if we have large samples, you should always expect to have some extreme values in there, right? This is just a function of getting a large sample. And this is kind of good. If I get enough people, I'm going to get those people who are hanging out there on the wings. So I'm going to get people who are, say, 4, 5, and 8 foot tall. Maybe if I get enough people, they're going to come up and they're going to be extreme, right? In terms of their univariate distributions. But hopefully, if I've got a sample that's large enough to capture some of those folks, it's robust enough so that it's not going to, those folks aren't going to swing things either way. If I got a sample of 30 and I catch someone who's 8 foot tall, that's when I have to be concerned, because it's going to start dragging things around. All right. So identification of univariate outliers. We're going to look at histograms. We're going to look at our z-scores. Also going to look at our box plots. You all know we've worked with box plots. Nice thing about box plots, you might think about, and I think about this sometimes. Boy, if I got histograms, why am I also getting box plots? Isn't this a little bit redundant? To some extent, right? Nice thing about box plots is I could play around with histograms in my binning to kind of start to impact the shape of that histogram, right? SPSS does it by default. And so if you like SPSS's default, source state is default or anything, you can say, okay, I like this, but the histogram that Basha puts together might be different than the histogram that I put together. We have this issue when we're running folks in the class who are using Stata and people who are using SPSS. The histograms look very different because the defaults for binning is different, right? And so we start to get into some problems there, and sort of a limitation of the histogram. Box plots are the same no matter what program you go through and capture them, or should be about the same. Midline is the median. Bounds of the box are going to be the first, the 25th, the first quartile and the third quartile. Between those two, that's your interquartile range. Whiskers are going to go out to the most extreme value that's still within 1.5 times the interquartile range. Anything beyond that is going to be indicated by points. It just standardizes everything so that I can look at a box plot and know exactly what these things correspond to. So it's good to have this in mind and be remembering what's happening and sort of what these different features of the plot correspond to. Okay. Anybody have questions about the box plots interpretation? We've done a lot of box plots interpretations, so hopefully this is all a review. All right, so what do we do if we've got univariate outliers? Check our entry. If that's a problem, we fix it. If it's a problematic variable, like we talked about, like, yeah, I collected this feature and wanted to kind of look at this, but no, I just say, Amanda, you're doing jury research, sort of like archiving, sort of things like that, and you really want to find that you're kind of really interested on sort of the dynamic of what happens if the jury is mostly comprised of sort of racial ethnic minorities, but there's only like just a very few handful of those juries that are like that. It's cool and would be kind of interesting to look at, but if you've only got, 5% of your total sample as that, then maybe if you're just saying, like, is this a minority jury? Yes, no. Maybe that's not a variable that's reasonable to conclude in there. You just don't have the balance, right? It's a dichotomous, but you basically have it's a univariate outlier. And so maybe we just exclude that out just because it's disappointing, but we just don't have the capacity to go through and actually get good parameter estimates based on sort of the characteristics of that variable. So thinking about excluding it. If I've got a case that's not representative of my population of interest, I just get rid of it, right? Like sort of the guy, the 65-year-old retired guy that's taking a French class just for the hey-ho heck of it. He's not relevant to sort of me understanding anything about sort of undergraduate income. So I'm going to throw him out and it's fine. Doesn't impact anything, okay? But if we've got those cases, right? You got a heavy cocaine user in there and that's good. They're interesting. You want to have that person's data in there, but you can't have them screwing up your whole study. We can think about smoothing procedures, okay? Here with smoothing, what we're doing is we're taking that outlying score, whatever it is, and replace it with a value that's 1 unit larger than the next largest score. So I've got someone who uses, say, once a week, right? And they're at the high end of the distribution. Then I've got someone who uses 5 times a week. I don't know, that seems like a lot of cocaine, but maybe someone is doing that, right? So they're way out there. Once we verified that's an actual score, maybe what we do is we take that and say, okay, well, 5 times a week is too much because you're way out there. We've got someone here that's once a week, and maybe we set you to the value that's like twice a week or something like that. Basically, we're smoothing. Rachel, you made a face. What are you, are you reacting to smoothing?
I was trying to figure out, I think I figured it out. I was just, with a value 1 unit larger than the next largest score. So I was thinking, well, why would you do that? Because it would farther away from Barker, but then I was realizing that probably that's
Yeah. We're just taking it and and bringing it in, right? Now, I thought maybe your reaction was because like we're basically making up data, right?
I just was having a moment.
Well, I also have a moment. Like, smoothing is a weird thing because we're saying like, oh, we're going to take you and artificially set you at the next. You're still the highest. Sort of, we haven't changed in your relative rank position in our data set. You've not changed. You're still at the top, but we've decreased the magnitude of that in, right? Now, this is a procedure that people use commonly, but it does mean like, oh, I'm changing the value. You said this, and now you get a value of this. And so sort of wanting to think about the consequences of that. Now, if we've got one person or a couple of people who are kind of out there, I want to keep them in there, this can start to be a reasonable thing. This is something that's done. You can do it. You always want to report this, right, that you've done this, but it's something that can be done. Now, sometimes, though, we're going to have people who, if I'm looking at, again, just substance use is a nice example because it's not a normal distribution. I've got something that starts to look at a pretty long tail, right? And it's not just one. I could take the most extreme and bring it in, but now I've still got sort of other people who like to what it, like now I'm shuffling the whole deck to bring things in, right? Now all of a sudden smoothing is less of a desirable approach because now I'm having to mess with a whole third of the sample that's existing out on my tail. Here's where we're going to start thinking about transforming. Okay. The distribution of this data is problematic to the point that it's going to throw off all my residuals and it's going to be an issue. So here, what I'm going to do, it's the difference between having distribution look something like this, right? Versus something like this. Okay. Smoothing here, I got a couple of weirdos. I want to keep them in, bring them in. Probably going to be okay. This is a whole different thing. Can't smooth that. The whole distribution is skewed, and we probably expect it to be skewed. So oftentimes what we'll do here is go through and sort of take a look at our transforms. Okay. So always important to start thinking about our univariate distributions and addressing these things before we start looking at multivariate outliers, because if you don't, the folks who are weird in univariate space are also probably going to come up as weird as multivariate space. So what we want to do in our screening, if we've got univariate issues, make those corrections before we start sort of moving into looking for multivariate outliers and things.
So just to make sure that I'm understanding correctly, with smoothing, you should only use it if like bringing those outliers closer to the center of the distribution.
Not to the center, just closer to the sort of the end, right? So
Closer to the end.
yeah, and yeah, not the center, because they're not the center. What we're going to do is bring this and put this person here and that person right next to it right there. So
Okay.
we're maintaining the rank order of these cases. We're just bringing it in, which is actually all that your transform is doing. It's just sort of doing this from a mathematical standpoint. Here, we're just assigning these cases back in.
So you should only do that if like moving those values won't overlap with other values that are in the
Yeah, you wouldn't. And now the problem is if you get a situation
then you want to do it.
like that, now I don't know, what do I do? I mean, you could think about it, right? I mean, if there's something that makes sense like this, what you want to do is always be thinking about your strategies and think about what's this going to do to my data and does this make sense? Could I stand in front of my peers and defend what I've done with these data, right? Here, that's kind of a weird kind of situation. But I don't know, maybe you just kind of stack them all up so they're right there. I mean, maybe, right? If this is your distribution, I certainly wouldn't want to transform the whole thing because that's going to make things weird and worse. Is this a problem? Do I got a big enough sample to where that's sort of not going to be an issue if I got sort of a couple people hanging out in the wings? Is that a big deal? If it is, though, maybe I just kind of crunch them all in and say, here's kind of some bigger some folks who are higher on the end. So again, no easy answers, right? Applied data analysis is almost always what's the least worst option in terms of what I'm doing, right? And so, yeah, different people will have different tolerances for what they're willing to do and fool around with data and things along those lines, right? But just wanting to be able to say, this is what I've done. Here's what I considered in terms of my options. This is what I decided was the least bad. And so this is what I went through and did. And if you're really concerned, run it a couple of different ways. Now, don't run it a couple of different ways and choose the option that you like the best. But you could say, if I run this, just leaving things alone, and then I smooth it and run it, do I get any real major differences? If I don't, then I'd be like, well, if it doesn't matter, then just leave it alone, right? Like, well, I went through and explored some smoothing options on this, which made some sense based on my screening. When I actually analyzed my data, it really didn't make a difference whether I smoothed it or not. So then don't do it then. Just leave your hands off of it. Then you can say, just I looked at the data the way I looked at the data, right? What you wouldn't want to do is then go through, look at like 7 different options, choose which one gave you the p-value you like the best, and then choose that one. That's not good, right? But, and in terms of screening, there's different camps and different philosophical approaches in terms of how we approach this, right? There are some people who are very much, yeah, do it sort of different ways to see if it makes a difference and things along those lines. Other people who are very much against that because it will result in cherry picking. Like, we're only humans and we're susceptible. We would like to not be, but like, I'm going to be really motivated to do the thing that lines up most with sort of the results I'm excited about, right? So just have a plan and then stick to that plan and try not to, oh, I looked at things 15 different ways and this was the only way that sort of the thing that I wanted to come up comes up. If that's what happened, that's a good sign that whatever you want to come up is not a reliable thing or something that's real. If this only happens in the magical world where I do this exact dance and recite this exact incantation, it means that you don't have a replicable effect and should know that and sort of not be very hesitant to try and publish something like that. Yes.
I don't know what it's called, how appropriate it is for like how people go about doing it, but I feel like that's sort of the process where like we'll have like DNA data and we'll have like a really like pretty continuous variable like scale from like 0 to 100, and they're finding a bunch of people are like marking 100 or they might be or like you know like a couple of people are doing this stuff because not and then they report going in and essentially like actually trying to like increase the variability in the data, which seems like a little uncomfortable to me, but I wasn't sure if that's like.
Well, I mean, it's part of the transforms will do that, right? If you got everything kind of stacked up and then a tail, so it preserves your rank order, but it just kind of spreads things out and gets things into a distribution that's more amenable to the types of analyses that you're working with. You just need to recognize that you're now working with transform data, not observed data, and sort of recognize the impacts of that. Yeah. Other thing people will do is sometimes we don't see this as much in our field, but people will talk about working with trimmed data. Has anybody ever run into this before? Yeah. Where did you run into it?
Well, I don't know if it's exactly the same thing, but in my undergrad lab, we were looking at censored data and ways to estimate what it would be if it wasn't censored.
Okay, cool. Yeah, there are certain types of regression models if you have censored data. And censored data is to say, like, I have ratings sort of 1, 2, 3, 4, and then 5 and above. right? Where we just kind of collapse it all. Those types of data require some special modeling to do appropriately, because two people with a value of 6 could be completely different in terms of, one might be like, oh, I'm a 7, and someone else could be like 15, right? So that's a little bit different. Trimmed data is where I say, okay, I'm going to go through, and what I'm going to do is I'm going to lop off, say, the bottom 10% and the top 10%. And I'm just going to look at sort of people right here in the middle, right? I'm just saying, for this model, I'm most interested in looking at what happens to like the main, like 80% of the folks. Now there's going to be folks on the extreme that they're doing their own thing. That's not what this is supposed to be looking at. What I'm going to do is I'm just going to trim the top 10%, the bottom 10%, and just look at this. Okay. This is an approach, and it's an approach that produces generally much cleaner data. Problem is now I've lost 20% of my sample, which is problematic for power. Also, sort of depending on if I really actually do want to generalize to all folks, or if I'm really actually interested in, again, clinical folks, we're typically interested in what's happening on the extreme. If I lop those folks off, then I've just looking at people with routine day-to-day misery, as opposed to sort of the kind of clinical stuff we might be more interested in, right? So it is an approach. We're not going to talk about it much here because you don't see it a whole lot in psychological data, but from a statistical standpoint, you'll often see this, and it's generally associated with cases where you've got more, where I've got 20% to lose and I'm fine with that, right? Type of a thing. So, all right. Transformation starts to become important if we're starting to think about like what's good for our numbers versus what's good for our interpretation. Problem with transformation. Some people really like transformation because it sounds cool back. Oh, I transform these data, right? You got an Optimus Prime situation here. We've got a whole new different thing. That's the problem. It's kind of now we've got a whole new variable that doesn't mean what we think it means, or at least how we normally understand it. Transformation, it complicates our interpretation. Because if I do this, I can no longer say, here's the association between X and Y. Now I've got to say, here's the association between X and the log transform of Y. Okay. Allie, do you know what PTSD is? I hope so too. And if I say, hey, here's a score on the PCL, do you generally have a sense for what that means in terms of stuff? Okay. Do you know what the log transform of PTS is or what that means? I don't either, right? It changes the nature. Now all of a sudden this variable that I had that I understand is now in a form that I don't understand, right? And so it starts to become an issue of interpretability. Yeah, I measured this thing. Here's the relation of X with the thing that I measured after I sort of changed it around in a nonlinear fashion. What that actually means starts to become kind of the crux of the issue, okay? Now, sometimes our transformations are necessary, and in some areas it's common practice, right? If you're doing alcohol research, transforms are part of the standard gig, right? And it probably, I would imagine, if you didn't, you would get in trouble. And most people understand what a log transform of the audit looks like or something. It starts to become currency that sort of people who do this understand what constitutes a high score versus a low score, things along those lines, right? But sometimes people will just go through and transform things just to transform things because they got a low p-value on a screening that doesn't mean what they think it's going to mean. And all of a sudden people started to transform stuff. And now it's hard to know what exactly you're looking at or what these associations mean, okay? Tabachnik and Vidal, pretty liberal in terms of their use of transforms. I'm less so, unless you have a good reason for doing this. I've become more warm to it, right? So long as you know what you're doing and what that means and you've interpreted it appropriately, cool, go for it. But oftentimes what you'll see is people will transform data and then pretend they didn't transform the data, and then you just talk about the relation between X and Y and so on and so forth. And you're like, nope, that's not what you're looking at. You're looking at a different thing that doesn't mean the thing that it originally meant. If you take the log transform of that, that's what you've got, but I don't know what that means. it increases the interpretation, or it should increase the interpretive burden on you to go through and account for that log for whatever transform you did and exactly sort of what that means. Okay. Common transforms, if I've got sort of moderate positive skew, a square root, right? So I've got my X variable, my predictor has some moderate positive skew. If I take all those values and I take the square root of those values, that'll kind of even things out a little bit. I've got a large positive skew, a natural log is something you'll often see. If I've got a large positive skew with 0 values, now I've got the natural log of my variable plus C, and C is equal to some constant. Generally add constant so that the smallest value is equal to 1. So if I have a scale that runs from 0 to 100 and I want to log transform that, I would actually take the log transform of my X variable plus 1. So now my variable runs from 1 to 101. Why do we add a constant to variables with 0 values? What happens if I try and take the natural log of 0? I don't get an answer, right? So we've got to go through, and so if you're not paying attention, what you do is you run a log transform of your variable, but if it has zeros, you have a bunch of missing values. You don't want that. You want to add a constant so that your lowest value is 1, so that you can then go through and get a natural log for all of those. Take a natural log of 1 is, I think, 0. So at least it'll go through and shift that over, okay? Severe positive skew, you can do inverse transform. So this is just 1 divided by the value, okay? If we take kind of L-shaped distributions with 0 values, so this would be like sort of this looking type of thing. Again, an inverse transform adding on a constant, because I can't take 1 divided by 0. That also won't give me a value. Negative skew, the square root of some constant minus X. And here what we're going to have is we're going to have a constant subtracted from the score, so the smallest value is 1. So if I got a negative skew, right, where things are going sort of towards the lower value, what I'm going to do is basically what we've got is a reflection. And I'm going to take some value, subtract my actual score to flip this around, because if sort of all of our transforms work good with positive skews, they don't work good with negative skews. So what we have to do is we've got to transpose our data, flip it around so my negative skew becomes a positive skew, and then I can run natural log, square root, inverse, and things along those lines, okay? Because if I just try and log transform a negative skewed variable, it'll make it worse. It'll make it really ugly. So what we need to first do is go through and reflect and then run a transform on that, okay? What does this do to interpretation? Yeah, ups, down, downs, up, everything sort of switches around. My signs are reversed, right? So you just have to keep a really good track of what you're doing, what it means. So now all of a sudden, if I have a positive correlation between the reflected log transform of X and Y, that actually means a negative association with, I can expect a negative association with the actual raw score, although what I've captured is not an association with the raw score. It's an association with the log transform of the score. All of this is indicating a nonlinear association, which I need to be keeping in my mind. It gets very, very complicated, and you can start doing a lot of gymnastics with trying to sort of provide reasonable interpretations of this. So transforms are a nice tool. They're a necessary tool. It's something that has a long history in statistical analyses. We just want to go through with our science. It's about interpretation, it's about theory, it's about understanding behavior, right? Which is different than some applications, some applied statistics where it's just, I don't know, I want to just predict outcome. And if I want to just predict outcome, if I want to say this thing predicts that thing, I could care less if it's sort of back, forward, upside down, or sideways, or the sort of fourth cubed root of something else, right? Doesn't matter, because as long as I have that, it unlocks the code and I understand I can predict. That's not what we're doing. So we need to be very careful and use this judiciously and understand the impacts on our data and the consequences for interpretation. Okay. So when we're thinking about interpreting our transform data, if I'm using ungrouped data, what we're looking at is the association between some variable and my transformed variable. Okay. So we say this is the association between extroversion and the log of aggression scores. What does the log of aggression scores mean? I don't know, but that's what I've modeled, right? So as long as you understand and are very clear about that in your reporting, can't talk about the association between extroversion and aggression any longer. It's the relation between extroversion and the log transform of aggression, which is a different construct and a different scale.
Well, if your scale is arbitrary, which apparently it usually is, I'm trying to argue with it, but like, it shouldn't make a difference on interpretation. But then I don't know where that kind of like leads to.
Yeah, I mean, like at best, sort of our stuff is, at least in psychological science, all our scales are probably ordered categorical data, right? They're not continuous. And so if I'm just thinking about this is the relation between this thing and some index of aggression, then fine, right? I've described our relationship between some measure, the measure was arbitrary anyway, but I would sort of take exception to the idea that it's all completely arbitrary, because if we're using measures that we all use, we know what high values are, we know what low values are. And if we're talking about, and if we ignore that and just say, oh, this is a relation between X and Y in my head, I'm just saying, oh yeah, so as this increases, sort of in a linear fashion, so on and so forth. That's actually not what happens. Anytime we run a transform of a variable, what we're doing is we're looking at a nonlinear transform, and that is, which has really sort of interesting implications in terms of like what that relationship looks like. I'm going to get to a slide here in a moment about sort of what that means, right? So certainly, and again, if all our goal is for prediction, then who cares, right? But sort of the concern is if I'm doing this and then so all of a sudden Riley's like, oh yeah, anxiety sensitivity is related to PTSD. Yeah, those two things are related. Well, not really, because if I just plot those two things together, they're not related in a linear way. There's something crazy going on, and I have to go through and do some stuff to that in order to get an association. And then what does that mean? Which should be the key focus of anything that we're doing, right? It starts to get more complicated, which is why I start to become, transformation is not something I jump immediately to. Sometimes it's necessary, but sort of I want to sort of think about sort of weighing this in terms of pros and cons, because it's not without cost.
I think I'm a little confused too, because like if you don't really know what the log means, but you can't interpret the original data anymore, are you supposed to interpret the log data essentially, or like interpret your log data as if it's the original data, but just stating that it's the log data?
Yeah, there's a couple different ways. Hold on to that, because the transformation you choose will start to have impacts on your interpretation. There are some that are more advantageous than others. Natural log is used for a reason, because within the context of regression, it retains interpretive properties, which is beneficial. So this is if we're talking about ungrouped data. If we're looking at group data, the relation, if I go through and look at transform variables, what I need to recommend or remember is that basically what I'm doing is I'm looking at differences in medians, right? So if I'm looking at college graduates and non-college graduates use of alcohol use or something like that, just because, and I log transform that, right? Now all of a sudden what I'm looking at is the difference not in the means of those two groups, but a difference in the medians. Okay, this is because our transformation changes the shape of the distribution, but not the order of the variables or the order of the cases. Basically, I go through and I log transform that. It changes what the distribution looks like, but everybody in there are still maintain the same rank order. So cases that are at the median of my untransformed variable are still at the median of my transformed variable. So basically what we're doing when we're doing group level, or think about reaction time. Reaction time is something that's notoriously nonlinear, right? Because we have some people who are very, very quick And then, so everybody's pretty quick. And then we get a sort of a tail out as people get longer and longer and longer out in terms of, all right, sort of Sasha, Basha, I'm going to go through and I'm going to show you like different colors, and I need you to press a button as soon as you see one that's green, right? Or a circle. Your ability to sustain that target sort of over time. So most of the times you're going to be fast. Sometimes you're going to be a little bit slower, right? You can't get there's a limit to how fast you can do it. You can't sort of get a score that's less than 0 reaction time. You did it like so. The only way you can deviate is sort of positively, right? And so what we'll go through and do is take those reaction time data and transform those into something that's reasonable. But if we're looking at sort of differences for people who say are taking stimulant medication or people who aren't taking stimulant medication, what we're going to do is say what we're doing if we're looking at a t-test with this, we're now looking at differences in medians as opposed to differences in means. Okay, so here's just random data I pulled from the interwebs. Here's untransformed data. We have a very clear skew going on with this, right? But if I go through and I transform these data, new distribution that looks much closer to what I might hope to sort of use. But everybody in this new distribution still maintains the same rank. The lowest person is still the lowest person. The highest person is still the highest person. Everybody who was at dead center, the median, 50% above, 50% below, are still at the median in my transform data, right? So I maintain this rank order. I just shifted things around in terms of the distribution with this, okay? But the thing to remember is, and sort of this is getting to your question, Katie. So here, let's say I have a relation, sort of calculated X and Y. Here's X and here's Y. We've got a clear nonlinear association with that. I could fit a line to that, right? But what's the problem with fitting a line to this? Is it gonna, the line gonna, what's a line going to do? If I fit a line to this, what's it gonna do to my estimate of the actual relation between X and Y? It's going to underestimate it. It's going to say, yeah, X and Y are kind of related when X and Y are very related. They're perfectly related. It's just in a non-linear way, right? But maybe I say, well, I don't want to do this. I want to use a linear model. And so what I'm going to do is I'm going to log transform X. So or take a square root function, I guess, of my Y variable. Okay. So if I go through and I square root Y, I've got a new association. Does a line fit that better? Yeah, not perfect, but definitely better, right? So what I've got is I can say, here's my association between X and the square root of Y. But what that actually means is not a linear. So X and Y aren't linearly related. X and the square root of Y are linearly related. If I look at the relation between X and Y, I've got a nonlinear relation. Anytime we do this, we're looking at nonlinear associations, which people will ignore or forget to address, but starts to become really important. If I want to say, what is the actual relation between X and Y? Well, I have to take a square root to model it in a linear model. But if I'm sort of taking, what I can do is I can take those coefficients and back translate that in and say, like, what's actually looking at is a curvilinear function with this, okay? So thinking about these types of things starts to become important when we're playing around with transforms. And yeah.
Prior to the end of this, but like what what's happening when you're doing the transformation and then you're now basically looking at median.
Yeah, if we're doing like t-test ANOVAs and things like that, yes.
So like those are like observed values. So like what does an interpretation of that like sound like?
I was just saying, like, I would say instead of saying mean differences, I would just say median differences in these groups, right? So I'd say you could still, I would say, sort of groups sort of I would probably be less focused on point estimates and confidence intervals around the transform variable, because that no longer means what I think it means, but I can still report effect sizes, right? I would say sort of group A scored sort of half standard deviation higher on the log transform of X than Y. So the results suggest median median differences in the median score across these two groups. Because again, the median is still the median, right? What we're doing here is we're looking at sort of median differences across these two groups instead of mean differences. Okay. And then when we get into thinking about within the context of regression models, that natural log transform has really nice interpretive properties. So if we can use a log transform, that's why it's so common. People often don't take advantage of it, but there's stuff where I'm comfortable with log transforms, natural log transform within the context of a regression, because I can still have a meaningful interpretation of what that looks like in terms of the association. And we'll talk about that when we get to that point. Okay. Last thing we're going to talk about here today is multivariate outliers. Okay. Here, what we're going to be looking at when we get into our regression screening, we're going to be talking about leverages. Okay. Leverage is the distance of a case from the centroid of the remaining sample. The centroid is just the mean of all predictors in multivariate space. Okay. So if I have the two predictor case, I have X and Y, right? I've got the mean of X and the mean of Y kind of exists sort of right here in my two-dimensional space. If I add a third variable, now I've got three-dimensional space, I've got a cube, my centroid exists sort of here in space. It's the mean of X, the mean of Y, and the mean of Z hangs out right here. If I get into four-dimensional space, we've sort of jumped into black holes and time warps and things like that, and I don't know how to sort of model that appropriately. But basically what it is we're talking about a centroid as the multi-dimensional point at which sort of the means of all your variables intersect with one another. Okay, so if we're looking at here in the bivariate case, right? We've got looking at the relation between height and weight. Okay, and here at the mean of height and the mean of weight for this sample is our centroid. Okay, it's right where we might have a multivariate outlier is something that's far away from that centroid. Now it's easy to see in two-dimensional space. Three-dimensional space, we can kind of wrap our head around it. As soon as we start adding more variables in the model, it gets harder to visualize. But let's say I have a case here where someone is 60 inches tall and weighs 220 pounds, right? That person's going to be a multivariate outlier, right? The combination of those two things starts to become distant from sort of where everybody else exists, or those sort of average level of the sample. Okay. But here, let's say we have someone who's 76 inches. So we've got someone who's tall and someone who's heavier probably than average. Okay. If we're just looking at height and weight, is this someone who's going to be a multivariate outlier? What do you think, Amanda? Just the height and weight. Is this person a multivariate outlier? Probably not. They're sort of someone who's sort of a larger person, right? But probably sort of on the margins. But if I'm looking at biological sex, what will turn this into a multivariate outlier? If it's a woman, we've got someone who's going to be way taller than sort of the average woman and sort of probably much heavier than the average woman, right? And so now all of a sudden, if we go through and add that third variable in, someone who was probably a higher value, but if we go through and add that third value here in three-dimensional space, now we've got someone who is for sure going to be registered as a multivariate outlier in this space, right? So again, thinking about different combinations about how all this stuff goes through and gets put together. Okay. We'll kind of see how this multivariate outlier thing kind of is working. All right. What we're going to do is we're always going to want to describe these multivariate outliers. We're going to use leverages, other indicators to try and identify which cases are strange in X space. But what we want to do is identify why they're statistically deviant. Okay. This is going to help us identify which variables are problematic, help us determine sort of what exactly is going on. Why is this person coming up? Are they part of our intended population of study? And sort of most importantly, starts to give us a sense for who is our solution unlikely to generalize to? Like, okay, we're doing pretty good, but people who have these characteristics are people who might not be adequately captured within our model. what we can do is we can start to hijack regression to start, once we find those multivariate outliers, we can start to do some cool stuff to go through and statistically isolate what specific combination of variables are causing that person to be sort of strange in X space. Okay. So again, was going through with Alicia and sort of doing some stuff with the thesis. She's looking at sort of uplifts, good things that happen to people, hassles, bad things that are happening to people, and sort of some other stuff, positive and negative mood and stuff like that. And sort of going through and looking at these leverage values, these multivariate outliers, people are coming up, and people who are sort of way high above average in terms of negative affectivity, like really, really high, but also really, really high on positive affect, which is a strange combination to happen together. And then like really, really low on hassles, like sort of floor effect on hassles, right? So we've got someone who's generally sort of looks to be sort of quite negative, but also quite positive, which can happen, but it's a weird combination. And then is also reporting like very, very low levels of hassles, which in this sample is these things are generally associated with high levels of sample hassles. So here's someone who's strange for these reasons, right? And so it starts to become important. What we never want to do with our multivariate outliers is to say, hey, here they are, and we threw them out without describing exactly what was going on, why we threw them out, and so that we can be confident in that, yeah, this was a good idea to go through and remove. So a little bit more stuff going into this piece of things. Okay. All right, that pretty much takes us to time. Thanks, everybody. What we'll do is we'll get stuff back to you for next week. But yeah, you can take a break off of stats. We'll go through and hopefully at least get realistically, so the internal optimist in me says, yep, we're going to go through and get through all this stuff by next week. We will not. So I'll still give you problem set 3 so you can have it over the break to go through and sort of play around with and do things to work on, but we'll be a while before this next set is due. Okay. Yeah. I don't know. I can give it to you today if you want. Okay. Well, I don't know. I can make it available. You can download it if you want to or not. So yeah, I'll just wait until we get a little bit farther through this so that people can go through and take a look at it. But yeah, this probably won't. This will end up pushing back due. So just so you can plan accordingly in terms of sort of the various things that you have on your plate. Okay. Awesome.